excavations. So there are 10 gradations, and every 10th gradation is marked with a circle, right? So in the literature, in the coefficient of this material. So this is a scale which was used. Weights were used from micrograms, from which is very popular even in Roman Empire. So the idea here is that you put your unknown weight here. The unknown weight times the length is equal to the known weight here times the distance to the origin here, right? The different kingdoms are using different weights, different measures, and all that. So in the earliest times, recorded times in modern era, Magna Carta of 1215, the British and the Scottish people, they decided that they should have the same system of units across the country. This was in early 18th century. And before the French Revolution, this was in early 18th century. And before the French Revolution, both the French colonies and the Portuguese colonies, they used the same system of units, the French system of units, right? So there was need to have same measurement tools. When I'm exporting something or when I'm importing off in 1800s, it's the late 1700s. So what they did is we know the diameter of the earth, right? So they tried to measure a large portion of this arc from North Pole to the equator, and then divide it by 10 power 7 so that you get definition of 1 meter. They actually sent expeditions on land, ship, and all kinds of transport modes to measure this arc. It sounds pretty ridiculous that you measure this 10,000 kilometers, then you divide it by 10 power 7 and then get 1 meter as the unit to be used, right? So there's a lot of large error bar which is expected from this. So, but this was the beginning of defining the meter in a very scientific way, right? So this went on in 1875, 20th May 1875. The meter convention was signed between 17 nations. This was done at BIPM. This was established as the headquarters of the weights and measures, which controls all parameters related to SI units. So all matters related to SI units are done by the CIPM, the committee, and the bureau, which is the headquarters of this. Then in 1889, they came up with the definitions for the meter and kilogram. And in 1954, ampere, Kelvin, and candela, second was also part of this. The prototypes for meter and kilogram were defined. These are platinum iridium discs, which I'll show a little later. So ampere, Kelvin, and candela were added in 1954. The name International System of Units, as we know, SI units, was defined in 1960. And in 1971, the 7th SI unit, the mole, was added to it to make the 7 things. The idea of this is the rest of the parameters, you measure anything, National Physical Laboratory, NPL. So the most famous one is NIST in US. It's the National Metrology Institute of USA. Right. Similarly, we have one national standards body, Bureau of Indian Standards. When we talk about standards, only people think that yes, BIS is the one, but BIS actually formulates the standards on paper, do this way, and then that becomes a standard, do this way, and then that becomes a standard for the country, and which there are ISO standards, which are the international standards, where again different countries accept that let's accept this way of measurement. Okay, so then that measurement technique is set up at the Metrology Institute and then disseminated to the accredited laboratories, legal metrology departments, and down to the shopkeeper level. Right. So this is what known as a traceability chain. So NPL being the National Metrology's weighing stones. Those stones are tested by legal metrology, and their equipment is tested at different accredited laboratories. For example, NABL is one accreditation body. So NABL accredited laboratories, they test, and we also act as a bridge with the international system. The way we do is so there is a blind sample is taking. For example, I'm saying that I can measure the percentage of carbon dioxide in a given sample, right? In a given unit volume of air, right? Meters, something, right? So, and at the end of it, it takes about sometimes up to 5 to 10 years. We pass this kind of intercomparison test, then this becomes a national primary standard, which is accepted globally. So each of the parameters which we have at NPL is actually billion. Right? That value is accepted globally in 102 countries, because each of these measurement capability goes through this intercomparison exercise, and then we globally compete with other nations to establish our national facility. right? At NCAN 1 is electrical and electronics metrology. We cover voltage, resistance, impedance, all kinds of impedances, AC, DC, RF, or all these are hospitals. It's not compulsory. The quality participation, whatever I'm saying is all voluntary. If somebody doesn't want, they say that like my equipment. So now the hospitals, the equipment which is being used, it's not being calibrated, tested. So the other one is this Bharati Nirdeshak Dravya, certified reference materials. Some equipment like the scanning electron microscope, TEM or XRD, right? These are heavy equipment. We cannot carry them to, say, an accredited laboratory or NPL to calibrate them. So how do we calibrate such equipment which are massive or very expensive? So these are different samples. So we have these right now. So about, say, 3 years ago, we were importing about completely, like 100% of our certified reference materials are imported from other countries. Now about 80% of our water testing is met with the local suppliers themselves. Gold, hallmarking. So for that, the gold, silver, we can have from 14 karat to 24 karat, like all the way, like we have the high purity materials. Rice, cement. Cement is being exported to Europe and Middle East. So these are again a huge number of these certified reference materials. We are working with Siddha and DAE so that we can bring in traditional medicine to the SI unit ambit. Right? So the sixth one is the Indian Standard Time. I'll show a little more about this. This is one of the best times which is available across the globe. Right? So this is one of, I'll show a couple of facilities which are best and recently developed. So our government has a push for generating 50% of our 2030 year. For 2030, whatever energy which is being used in the country, 50% has to be green energy. So for that, solar energy is one primary focus, testing these things currently. The other one is that like the environment monitoring equipment. I mean, not to scare, but just to say that like the practicality coming from Delhi, humidity is there, less dust levels are there. Now when we're bringing that equipment, is it really working in our conditions? Somebody has to test them. So we have set up the Asia's first facility. Right. So this is again operational. This is Asia's first facility and world's only facility, covering all kinds of environment monitoring equipment. You call it OSEMs and CAMs. So these emissions as well as ambient air monitoring equipment is all completely tested, certified. So now the government has mandated that like every single pollution monitoring, environment monitoring equipment used in the country has to be tested, certified within the country. So this we have the facilities up and running now, right? So mentioned about the SI units, mass and length. These were one of the earliest ones. So this is a platinum iridium disc, and this is a scale bar, meter scale bar. So each country has a copy of this, and when we go to the shopkeeper level, whatever 1 kilogram weight is there, that is a replica or copy of this one eventually. It's traceable to this, our platinum iridium. This is a national prototype for kilogram NPK 57 for India. And similarly, copy number 4 is the platinum. We don't know. There is an error which is coming because of the width of the tick which is there. So these are the things like how precisely you want. We use verniers and other things when we need high precision things, right? So to avoid such errors, the world over in 2019, they agreed to redefine the SI units. Now SI units are not measured with respect to a prototype, right? If we want to measure kilogram, we don't measure with respect to a known 1 kilogram weight. What we do is the units is now assigned to a universal constant, whose value is very well defined, whose value is very well defined, very well accepted, both theoretically and experimentally. So now what we do is we remove this pan, and we replace it with a coil in a permanent magnet, quantum definition, quantum standard, right? And similarly, like so, when you do so, what we are doing here is we are comparing the virtual mechanical power to the virtual electric power. F equal to mg is equated to the electrical power, which is given in terms of the current applied, the length of the coil, and the magnetic field which is induced in the coil, right? But now, the magnetic field measurement and the length measurement can have uncertainties. To avoid that, we do a second measurement can have uncertainties. To avoid that, we do a second measurement in which we remove this unknown weight, which we are moving it up and down. Now you replace this BL in this equation with this U by V, right? And then, as I mentioned, this U is basically related to the Josephson voltage. You get those constants here, von Klitzen constant and other things like, so this is again related to the quantum Hall resistance. So
V and I?
So the I is again quantum standard. We can go parts per million level easily, right? So, and the voltage.
Limited by thermal fluctuations?
We do the, V and I, we use, V and R we use. Quantum Hall resistance, we can get with parts per billion. And the Josephson voltage, we can get it with, similar levels, like at least microvolt level in 1 volt, even better than microvolt. You can go to nanovolt per. So
what is the short noise effect in that I?
We take care of all those things. And at the end, the mass will have at least 10 power minus 6 error bar. So in 1 kilogram, we can measure with 1 microgram. That's the best which is available currently.
So then the velocity is
velocity is by the interferometry. The length is measured with change in the length and time. So the time goes to the atomic clocks and the length to interferometry. So both are again quantum definitions.
Servo motor or something that moves it up and down.
Right, right.
And the servo is controlled in a way, so that, but you don't care about that because.
No, we do it at a very precise sinusoidal motion, right? So that's what we do here. Like, so and that's where the curve comes, and then you measure it, and then you go to the lowest values, and then operate it at that positions, right? And the entire thing goes into this is the 2-pan balance, which is modified, as I mentioned. So this, we are working for the 100-gram balance. So this whole thing goes under vacuum, so that like all the effects are reduced. Right? So this is just to give the complexity. Like, so this one Kibble balance, we should have a Josephson voltage standard, quantum Hall resistance, an interferometry for length standard. You need temperature standard. You need local measurement of the G, small g. Right? All these things go into one single unit to give a high precision measurement technique. So this is one at NIST. This one is from headquarters, the BAPM. Just look at, like, these are 2 people standing. So there's a 700 kg magnet, permanent magnet, which is here. And then you have all the robotic arms and all that movement, everything is included in this. So there's a coil which goes inside this permanent magnet up and down. Right. Similarly for the.
I have a small question.
Yeah, please.
So when you said up and down, so that also I wanted to know. So how is it aligned? Meaning the table is aligned. The magnet has to go up and down that direction.
No, permanent magnet is fixed. So the whole thing is in engineering. So there is a slot which is made in which this coil moves up and down, and it should not wobble, and the magnetic field has to be uniform.
So I mean the alignment, how is it aligned? Meaning the point is that you said that mass is measured to some 10 to the minus 5 or something like that. So the vertical direction has to be better than 10 to the minus 5.
Absolutely.
Right.
Right.
So how you align it?
That's all goes in the engineering, right? That's what goes into the complexity of this whole thing, that the coil should not wobble, it should go vertically up and down, and the magnetic field also has to be uniform within that. So the entire design time goes into designing and qualifying that.
That right. I understand. But I want to.
We do the
okay.
Right. We do it with the robotic. I mean, basically it's all in the mechanical designing, right?
Okay. Yeah.
Right. We can discuss later. Right. Okay. Right. Similarly, the temperature, the Kelvin, is measured through this acoustic gas thermometry. It depends on the speed of light, speed of sound inside the gas, right? So that C is proportional to square root T. So we measure the C, or the velocity of sound inside a gas which is filled inside this asymmetric cavity. The acoustic modes are measured in this, the resonances are fixed, and then we apply RF fields and then measure the velocity of that, and then from that we deduce the temperature, right? This again shows very high precision and a very broad temperature range for which like this works, right? So this is time. We were the 5th country in the world to have our own time standard, which is the cesium fountain way back in 2013. This became the primary standard contributing to the TAI, the International Atomic Time Calculation. Right. So this is all the bunch of electronics which are all built in-house, and then this is the optics on this table, and then the magneto-optical trap is shown here. So basically you trap the atoms, cesium atoms, kick them up and into the top. So before, I mean, there is a cavity here, RF cavity, the frequency applied, and then the frequency is tuned very precisely, and you monitor the absorption of this beam. So when the atomic beam is going up and down, like so, you measure twice, and from that, like you deduce the precise absorption frequency, and 1 over time, like you keep repeating this, and 1 over frequency is basically the time which you get. Right. So we are working on the next generation clocks, which is the optical clock. So the cesium fountain works on the RF frequency. The two levels which we use are RF frequency, but that's about 9.1 gigahertz, 9.19 gigahertz. But here we are going towards ytterbium ion clock, which is in the optical frequencies. So we are going from 10 power 9 hertz to 10 power 15 hertz. So we are expected to have sub-hertz to at least a hertz uncertainty in 10 power 15 hertz. So that leads to enhancement. Now about close to 5% weightage is given to our thing. Not just the bank of clocks, the way our algorithm to steer the clocks. Once in a month, we keep giving the data every 15 minutes to the BIPM. And once a month, we get the over that. So we have an algorithms which we take the average of it, and that ensemble average is what we give, what gives us this precision.
So this is the uncertainty measuring.
This is uncertainty. Right. Okay. So we also developed this disciplined oscillator. So for example, we give it to NIC, right? National Informatics Centers or stock exchanges. So we also give time to ISRO. ISRO needs nanosecond accuracy. The stock exchanges need microsecond. For our regular use PCs and all that require millisecond accuracy. So we provide different calibration and testing. So right now, as I mentioned, like we are buying these very expensive dilution refrigerators, and we are blindly trusting that, like, yes, they're operating as per the specifications. Electrometers, thermometers, like there are several other sensors, gravimeters, right? There are gyroscopes, all these things come in. Like, so when we talk about communication, we need classical sources, non-classical sources, as well as non-classical light detectors needs to be calibrated and tested. So eventually everything needs to be chip scale, handheld, compact, and energy efficient. So towards this, when we are working, we need to standardize things. We need to develop techniques to measure these precisely, each of these parameters, right? So we work on these things at NPL. So one of the things which I'll show you is a hot rubidium atom based, right? So we don't want complicated low temperature stuff. We also need something which is portable. So for example, Israel uses similar things for detect rubidium vapors inside the cells. Now we are making these cells also within the country at NPL. We make these and give it to DRDO and other organizations. So now we prepare these states. There is a pump and a probe beam. When the pump is there, like, so we induce this electromagnetically induced transparency. There are two different pathways to excite to this. Either you come from this state or from this state, right? These two interfere destructively, and you get this absorption minima in this case. So this is it's called the EIT. We use that phenomena and then calculate how much is the dip right. So this is how the structure, I mean, the lab looks like. It's an optical table full of these things. We're trying to miniaturize it so that we can take it to the field. Right. So we showed that you can actually mix different RF frequencies within this. So you can use these vapor cells, the Rydberg atomic levels, to mix these RF frequencies within these hot rubidium cells. This is one example where I'm not sure. Okay. So what is happening is the student is playing national anthem on his mobile phone, which is played as a RF signal onto modulating RF onto the detector vapor cell, and then gets modulated and then the modulated signal is launched into an optical fiber, then decrypted, and then played on this speaker here. Right. So this is to demonstrate that we don't need non-classical light sources to do quantum communication. Here the encryption is in the rubidium atomic levels, and unless we know what are the wavelengths which are used for exciting these and the RF which is used, it's difficult to decrypt it. So, but we can use the existing optical fiber, the classical optical channels, to use this communication. Right. So just I'll give you one example of single photon metrology. For quantum communication, as I mentioned, we need to get the single photon sources, non-classical light sources, detectors, both needs to be tested. So we do this by measuring like each of these things, like so what are the optical fiber losses, and everything needs to be calibrated very precisely. So there are coming from each of these connectors, the couplers, everything needs to be tested. So we do all those things, and we also develop our own non-classical light sources and detectors, right? So how do we do the non-classical light sources? One of the things which we use is using these so-called metamaterials. So the metamaterials are materials which whose epsilon and mu can be designed as per our wish. So for example, naturally existing materials have a given epsilon and mu. The epsilon tells how the material interacts with the electric field of the light or responds to the electric field of the light, and mu, the magnetic permeability, tells us how the magnetic field of the light influences the material, right? So these epsilon and mu can be either positive or negative. So depending on that, if you plot mu versus epsilon, in the second quadrant you have metals, the epsilon negative, and in the second quadrant you have both epsilon and mu are positive. The fourth quadrant you have epsilon is positive and mu materials as per our wish, by having sub-wavelength featured scattering elements or components inside this. So just to give one example, how do we do that? If we take two different materials of epsilon 1 and epsilon 2 with thicknesses in D1 and D2 such that lambda is much larger than these thicknesses, then the incident light in one wavelength, it will not see each of these individual layers, but what it sees as an effective medium. Right. This effective medium has epsilon and mu given by these approximate values. But now the electric field can be either parallel or perpendicular to the layers, depending on that. Like if you look at the continuity of the electric field and the first derivative, you get these two equations. And for epsilon E perpendicular to the layers, you get these two expressions. So from this, from this direction, it acts like a metal. So it reflects all the light active index, right? So this n omega by c, so n is fixed, nx, ny, nz. But if you have epsilon xx and epsilon zz to be different, and they are, one is positive, other is negative, one is metallic and other is dielectric, for example, then you get these hyperbolic dispersion profiles. So once you have this, the important point is, unlike the maximum k value which is defined in a homogeneous medium, here infinite k is also in a load mode within these materials. Right. So we use that kind of material to have a single nanoparticle. It can be a nanodiamond. We also showed it for a single quantum dot, so that all the modes which are the single nanoparticle is emptying in all directions. So these are all L-load modes within this layered structure, hyperbolic structure, and they're all collected within this medium. And then it comes to the air, for example. So these are all evanescent modes. So to make them focus, like we use this patch antenna on the top, so that like we can design it to have light emitted in particular directions. So this is designed for a 15-degree angle cone. So we showed that we can also have quantum random number generator based on these few photon level sources. Right. So we also work on different material aspects. For example, when you put a nanoparticle, a single nanoparticle, and then embed them in multiple layers. So there's oxygen diffusion, all these things happen, and the stability of the quantum dot itself, or even the nanodiamond itself, will get affected. So what we do is we studied a large number of materials and showed that like basically hafnium dioxide and gold give a good combination where we can protect and we can get single photon emission from these structures. We also working on this single photon detector, which is a superconducting nanowire. So we make these thin films of 5 nanometer uniform thickness, and then we pattern using FIB or electron beam lithography, these meander wires. When a photon falls on this, it changes to the normal state, from superconducting state to the normal state, and gives a voltage pulse in the external circuit. Right. So we developed these things. This is one thing which Professor Shashi is here. So this was work done at TIFR. This is a silicon photomultiplier which was designed, and the prototype was made at Bell. So he showed basically photon number resolved measurements. It's not presence or absence of photon, but can you also say how many photons are there? Right. For communication, this is one important thing. So they're very specialized detectors, like the transition edge detectors, which are being designed. But what we showed is that this basically, if you have an array of APDs, so if you diffuse the beam, depending on the counting the number of pixels which are triggered, you can actually say how many photons are there in the incident beam. So this was Professor Shashi's idea. So just to say that, in my own work, just to give one slide. So the metamaterials, we use it for physics. So for example, latest work is on invoking. These are gold nanodiscs in which we invoked magneto-optical properties. You can design it. So each of them will have a localized surface plasmon which is excited. But when you decide the period, when we design the period such that the localized plasmons in each of these disks, they couple and then form a lattice mode. So the mode extends entire lattice. So in that case, we showed that the in-plane Lorentz force can be enhanced, which leads to Verde constant of the order of 10 power 7 degrees per Tesla per meter, right? So this is huge, as high as any material reported ever. So these just non-magnetic gold disks. So you can invoke these magnetic effects. So this is the kind of physics which we do. We also do from single photon emitters, as I showed, to single molecule detection. This is again interesting. This is a cotinine, which is a residue of nicotine. Nicotine lasts for about 1 to 1.5 hours in the human blood or urine or saliva. However, cotinine lasts up to 12 hours. So it is a better detector for tobacco abstinence. When we made single molecule detection using SER's surface enhanced Raman spectroscopy, and we went to the AIMS, they said we don't need single molecule, even micromolar is good enough for us. So there's a gap, so we need to look at what is needed and what is actually capability of it. We can use it for some other application, but for biomedical applications, micromolar is good enough. So we showed that and working on commercializing it, right? So just to summarize, metrology is the science of high precision measurements. It forms the backbone for the quality infrastructure for any country, right? So there is a global network of national metrology institutes, which bound by the mutual recognition agreement. So we all work together in setting up standards for the country and for the globe. So quantum metrology is the redefined SI units. This is an emerging area, but once we have these, they also form essentially cover the metrology needs of the quantum technologies which are evolving more rapidly these days. So I showed briefly nanophotonics, metamaterials, how they can contribute to the future metrology aspects. So you can miniaturize this. I didn't show. We also work on atomic ships. We are working on atomic ships. Instead of having big chambers, can we have handheld atomic clocks eventually, right? Just to acknowledge, these are people, ones in blue are currently working in the lab at TIFR. The ones in blue here are the theoreticians I collaborate with, and these are colleagues from NPL whom I collaborate with, right? Thank you very much.
Thank you very much. And now we really have 5 minutes for questions. So I'm sorry I cut off Pata in the middle. So if you want to start off the questions,
we'll discuss.
Actually, very nice presentation, and this timekeeping is one of the wonderful things that I see. So while you are providing time, very accurate, measurement of time to the country, are there any efforts in the direction of providing position?
Right. So that's a domain of ISRO. So right. Disciplined oscillator. So initially we made it for the GPS. It's just the frequencies which are different, right? And the bands L1, L, whatever bands are different for the GPS and the NAVIC. So we also made the disciplined oscillator for the NAVIC frequency, so that dual frequency. We're also working with Bardhaman, where can we correct the time locally on the chip, so that at different frequencies, like we collect the same time information and then correct it, so that like we can get better time and positioning accuracy. Okay.
So there are
Yes.
Yes, please.
You have shown a demonstration of the quantum communication, quantum encryption. So what protocol are you using there?
So we tried the standard protocols like PSK and other things. Like, so there are 2-3 different protocols which were used. Right?
So not something like a QKD protocol.
Not the QKD protocol yet. The whole idea is that like we don't need to go there. We can still use the classical the channels and use the quantum for the encryption decryption. That was the idea of it.
And also you had, with regards to the Hubble balance explanation given, wouldn't you also have to measure the gravitational, wouldn't you also have to measure small g?
Yeah, that's what I said. I mean, I verbally mentioned, so the small g has to be locally measured
So
at
you
every
do that
location.
yourself, or
We do it in the lab, right? So even if we take it from this room to one floor up, like it changes. So we need to take those corrections or measure it in that location. Sorry.
You mentioned about the single photon. So how to detect the single photon in lab actually, what kind of device you can use?
Right. So the established or the common way of measuring it is you put a beam splitter. If there is a single photon, it either gets reflected or transmitted. Now you put 2 single photon detectors, like avalanche photodiodes or superconducting nanowire based detectors, and find out what is the probability of finding a photon at a given time in both the detectors. At t equal to 0, that is the path length in this path and this path are exactly equal, only one of them should show. Right? Only one of them will show the photon and the other detector should not show the photon. So the probability of finding photon in both the detectors is 0. Right? But from the Poissonian statistics, you have 1 minus 1 by n average n. Right? So from that, like you can say that if you have one photon, is 1 minus 1 by 1, so that is 0. But if it is 2 photons are there, it goes to 0.5. So between 0 and 0.5 probability, you accept that like you have predominantly one photon. If it is 0.5 and 0.75 or so, like you say that like yes, you have 2 photons and right. Sorry, yeah.
Sir, I wanted to ask you, like, for the accuracy control for different experiments that physics does and different experiments in lab and for different technologies that it is applied. So the way to control the accuracy there, how is it like always feasible? The machines that you are making, it is possible that is not fit into that experiment or its structure is not possible. So
I did not quite get like, so you're talking about like
the accuracy control in experiments and technologies might be very case dependent, and then the structures or the designs that made for the perfect accuracy control is not supporting there. So isn't it very case specific or how you
so typically we aim for the lowest uncertainties possible so that we can cater to the larger thing. So in case of Hubble balance, for example, one example is that like so we make different things. Eventually what we need for the primary standard is 1 kilogram, right? But what we made first is a 10 kilogram. It can work from say very precisely from microgram to say 10 grams. Right? Then we are now working on optimizing the 100-gram thing, and then we'll go to 1 kilogram. Each of them is important because each of them will have a different uncertainty ranges for different ranges of the weights, right? So it's not, there's no one single system which works for the entire range.
I wanted to really say
Sorry. We are a little bit tight, so I thought maybe we could take, I can see you have many questions and so do some of us. So maybe I'll sort of formally close the session here. Please, everyone should join us for tea outside and we can ask him more questions at that point. Don't forget your questions. Please be done. just before we end, we have a small token of this is the one. Yeah. So this is on behalf of IISER.